Oh, and Erin, are you okay recording the webinar or would you prefer not to?
That's fine.
All right, hello everyone. Thanks for joining. We're just going to wait like 30 seconds to let people filter into the webinar and then we'll get started. So thanks for your patience. If you're just joining us, we're going to wait just a few more seconds to let everybody hop on and then we'll get started. All right, I'm going to go ahead and get started while people are still filtering in. I know we've got a lot to get through today. Thank you for joining us for the November US MAP webinar. We're excited to have you here. My name is Harrison Dreves, in communications at the National Renewable Energy Lab, and I'm going to be making sure today's webinar runs smoothly. So I've just got a few quick technical housekeeping items before we get to the actual presentation. Everyone is going to be muted. We'll have enough people on the line that unfortunately we can't just have an open discussion, but there are going to be chances for interaction. In terms of listening, you've got two options for audio. Most people use computer audio. It works great 99% of the time. But if you are having issues with that, you've always got that phone option. You can switch by either using the audio button in the bottom left-hand corner of your screen. It kind of looks like a set of headphones. Or if that's not working or confusing for some reason, you can always just leave, rejoin, and choose the phone call option when you connect. In terms of Q&A and questions, we are going to be doing Q&A at the end of today's webinar. We are going to be using the Q&A panel in Zoom to do that. Don't get confused with the chat panel. Chat panel has one speech bubble. Q&A has two speech bubbles. So click that Q&A box, pop that up. That's going to be how you submit questions for our speaker. We are going to try and get to as many of those as we can, and you can submit those at any point during the presentation. So if a slide piques your interest, go ahead and put that question in, and we will ask it when we hit the Q&A period. I've also enabled upvoting for questions. So if you see a question in that Q&A panel that you agree with, you'd really like to hear it asked, go ahead and hit the little thumbs up icon next to the question, and that'll kind of bump it up our priority list for asking questions when we get to Q&A. The chat panel is also enabled. Please use that if you're having any technical issues. I'm going to be watching that all webinar, and I will be helping to troubleshoot to the best of my ability any issues that come up. All right, with that, I'm going to hand it over to Tim Guillen, who will be introducing today's speaker. Tim?
Thanks, Harrison. Can you hear me okay?
Yeah, you sound good.
Great, awesome. Well, thanks for the introduction. For those that don't know me, I'm Tim Guillen. I'm the US MAP Executive Board as the Industrial Advisory Board representative, and I'm also the head of R&D at Tandem PV. And it's my pleasure to introduce Professor Erin Ratcliffe today. Erin is an associate professor of chemical and environmental engineering at the University of Arizona. And I think she's got a really exciting talk for us today about electrochemistry and perovskites, and I'm really excited to learn. So thank you for joining us today, Erin, and I'll let you take it off.
All right, great. Thank you very much, Tim and Harrison. It's a pleasure to be here. I've really enjoyed this seminar series and as a watcher, and so I'm excited to get to tell everyone today about some of the things that we've been doing. So I want to go ahead and kick things off by just remembering to acknowledge our sponsors. The work that you're going to see today started out of an Office of Naval Research effort dating back to 2020 in the middle of COVID, and now has moved into a CETO-funded SIPS. And the last thing I want to say, just to make sure I get it out there and you'll see it again, is we are looking to partner with all of you. We want to look at your materials and see how our electrochemistry can help predict both device performance as well as stability. So with that ask, I'm going to go ahead and get started. And so I like to try and have an outline just to keep myself on task here. And so what I really wanted to do is just kind of frame the discussion a little bit about the ideas of defects and eventually ion migration that we know is a major problem in metal halide perovskites. Right? And so if we just think about this from a very fundamental perspective, right, there's intrinsic defects, point defects, phase transitions that arise from chemical and physical properties of the materials themselves. And then, of course, as soon as we start to interface the perovskites with either hole transport layers or electron transport layers or buffer layers, etc., this introduces a different form of defects, a surface defect that can contribute to surface recombination. And then, of course, these materials are very dynamic. And so the defects can evolve with time. And so this can be from environmental effects, heat, light, or oxygen, water, so forth. Right, and that these defects can arise across a number of different length scales, and that are very mobile, established to be very, very mobile. And so thinking about how to characterize the defects under relevant device consistent electric fields is also a critical component. Right? But I'm an electrochemist by training, and so when I think about defects, and in perovskites in particular, most of these defects are going to be electrochemically active and mobile. And of course, some of them may not matter because of the defect tolerance of the perovskites, and really it may also depend on where they lie on the energy band diagram of the material. But the general consensus in the field is that these defects are going to contribute significantly to the stability of the material and ultimately the long-term performance of a device such as a photovoltaic. So this lets us ask a very simple question of how many defects are there? And so we can start with just a very simple thought experiment. And what I'm showing you here on the right is a high resolution TEM out of the group of Dinsung Wong at North Carolina. Right? And if you look at the length scale, again, this is when we first got going in perovskites in 2020, right? What we really have here is domains on the order of about 20 by 20 by 20 nanometers. And so if we just make an approximation and we assume 1 or 2 defects per face of each of these grain boundaries, this quickly leads us to defects on the order of about 10 to the 18th defects per cubic centimeter within the bulk side of the perovskite. Right? And so if we think about defects, right, it really depends on the material. Right? And so what I'm showing you here is a literature survey from 2022 of just how many defects are reported in a simple material like MAPI and across 4 orders of magnitude. Right, and that this changes as well when we switch to these other materials such as this triple cation, the cesium FAMing type of complex. Right, but the other thing I want to call your attention to is that it not only depends on the material and who's made it, but the number of defects that one reports often depends on what length scale you look. And as a characterization protocol, right, it also really depends on the approach that you use. What are your defect tolerances, or what can you truly detect depending on the characterization tool that you use? Right, so we have defects that we would like to measure, right? And then if we want to connect this to device performance, what we really need to do is answer the very simple questions of what's the origin of the defects, why are they there, where are they on this energy scale, and how many are there? And those questions are simple to ask, but are very, very difficult to find out. And so what we really need is an ability to quantify the number of defects with high energy resolution, less than 10 millielectron volts, and monitor these redox processes, these redox active defects under the device relevant electric fields. So that's what I'm going to tell you about today, is how we do this in my group. Right, and so we're going to start with how we draw an energy band diagram of a perovskite and how we get this very simple experiment to now understand exactly where on this energy scale with respect to vacuum, the valence band and the conduction band of the perovskite lies. Right, so we could certainly start with a conventional approach like photoelectron spectroscopy. And I'm showing you 2 examples here of UPS, or ultraviolet photoelectron spectroscopy, and inverse photoelectron spectroscopy. Right? But I want to draw your attention here to the resolution of these techniques, in particular along the energy scale, right? Because of the detector capabilities of the techniques, we're really on the order of about 0.1 electron volts with these capabilities. The other thing is that this is an ultra high vacuum, not under a device relevant electric field and not under op grounded. So what if we want to increase just the energy resolution, we can turn to another technique that's very, very simple, electrochemistry. So I'm just going to walk you through a semiconductor electrochemistry primer here in 2 minutes, all you need to know. So if we take a semiconductor and we interface it with an electrolyte that has supporting ions that allow us to drop the electric field at that surface, right? We do this with what's called a 3-electrode technique. And here we have what's called a reference electrode, which is a known chemical redox reaction that allows us to know exactly where we are on the energy scale, and then can connect this directly with respect to vacuum. Right? The other thing that this technique does is that when one applies a voltage, right, and includes something like a redox molecule, such as ferrocene, a very well-established redox couple, again, now we have an energy-dependent probe for different energetic states. And the key thing here to remember in electrochemistry, and specifically semiconductor electrochemistry, is that current will only flow if there's an available state in the semiconductor to participate in the charge transfer reaction with the redox molecule of interest. All right, so what does that mean? If we take a series of materials that, let's say nickel oxide, something that has been, very, very highly characterized, and we know that it has a very exquisite surface chemistry, right? And this can depend on how it's processed, right? So is it sputtered? Is it a nanoparticle? Does it come from a sol gel, right? The power of the electrochemistry approach is that you can see how much energy resolution we can get, right? This is showing you approximately 9 different nickel oxide films, or 8, I can't count and talk at the same time. But what you can see here is that you really get differences in the redox potential, or in other words, the onset of the states that are available to participate in the charge transfer reaction is very different in terms of about 100 millivolts with that 0.1 electron volts that you get in a UPS experiment, right? But we can tell very, very clearly that these are different, right? And so again, in semiconductor electrochemistry, you're not going to see a charge transfer to a redox species such as ferrocene unless there is an available state to inject or extract. Right, so let's take this technique and turn it on to perovskites. Right? And the challenge here with perovskites, of course, is that they're soluble in almost every solvent, right? It's very difficult to find a non-solvent. And so what we did is we actually just switched to a solid state approach. And so we use a gel electrolyte. This has about the consistency of like a cellophane film, very, very thin, right? We can include our counter electrode and our reference electrode, right? And so what this strategy lets us do is effectively make a rectifying half cell, like a battery, right? So in a battery, you test the anode and the cathode together. In a photovoltaic, you have the top contact and the bottom contact, and you apply an electric field. What this half cell does, if we take the battery analogy, is let you look at only the anode, only the oxidation process, or only the cathode, looking at only the reduction process. And so that you can basically understand how your device is performing, but with a direct correlation to that energy scale that you get from that reference electrode. Right? So again, it's not an equilibrium experiment because we're going to apply voltage and we're going to look at current. So this is really an under operation, right? And so the other thing that's really important about this technique is because it's not dissolving our perovskite, we can peel off our solid state electrolyte, and now we can do all of the post analysis. So we can put this in and look at the surface chemistry using X-ray photoelectron spectroscopy, right? Or we can look at it in situ using what we call spectroelectrochemical methods. All right, so with this approach, we take our perovskite, and I'm going to show you just a really simple example of a perovskite on ITO. Right, and so now if we apply a voltage, so as we go across this, oxidation is on your left and positive voltage, and reduction is on your right. And I follow the US convention, so cathodic current or reductive current is in the upper right-hand corner. All right, and so what you can see from this on our energy scale with respect to our reference electrode, or on the top for reference is with respect to vacuum, right? We can see regions where we start to see a higher amount of current density or current flux, and this indicates the onset of the valence band or the conduction band. And so by drawing these red lines on here, I readily acknowledge that this looks very arbitrary, but I want to promise you that it is not, right? And so the way that we know for sure that this is not is that we're going to do a very simple spectroelectrochemistry experiment. Right? What that means is we're going to take our solid state device stack, and we're going to put this in a UV vis spectrometer, shine light through it, and we're going to monitor the absorbance as we change the voltage, or effectively as we go on the energy scale, right? So here comes the light. Let me put my pointer here. Hopefully you guys can see that. You can go through the lights and you monitor the absorbance, which is shown over here. All right, so I'm trying to keep my energies consistent for you. So this blue arrow at the on the cyclic voltammogram on your bottom left shows as we go out in negative, which is the equivalent of going from mid-gap of the perovskite up near the conduction band. And once we cross a certain threshold, this is where we start to see a change in our absorbance. Okay, and so this change in the absorbance is indicative of electrons being injected from the underlying contact into the conduction band minimum, right, which changes the absorbance, right, effectively bleaches the absorbance. And so if we reference a single wavelength, what we can do is now look at exactly where the onset, or if we take the derivative of that plot, the onset of that conduction band minimum is with a very, very high energy resolution that we cannot get from photoelectron spectroscopy approaches. All right. And so how sensitive is this? And so just to give you an example, what I'm showing you here is 3 different formulations of triple cation. The near stoichiometric one that makes about a 19% device in our hands. And then if we just add a little bit extra, about 2% excess FAI or excess lead iodide, right? You can already see that we're able to not only see the differences in the conduction band minimum with the slight changes in the chemistry, but as well, if you look closely, you can see a difference in the distributions of the onset in this density of states. Okay. All right, and this is a really, really powerful capability because it lets someone know immediately where on this energy scale the effective states are that are going to participate in the conduction of electrons or holes, right? Likewise, what it lets you do is it lets you understand how different interface modifications, maybe you've put a phosphonic acid on your HTL, maybe you've thought about trying to add a buffer layer, maybe you've tried to add a 2D perovskite. This capability will tell you exactly at what energy position electrons or holes start to move across that interface. And it agrees very, very nicely with what we see with, like I said, photovoltaic performance, as well as time resolved photoluminescence measurements. All right, so what I'd like to really do for the good chunk of my time is I want to talk to you about how we characterize defects. I'm going to show you 2 case studies, and I'm going to go into the details of how we do this with these 2 examples using a high defect MAPI and a low defect where we've had to change our methodology. All right, and then what I'm going to do is I'm actually going to show you at the end a few examples of where we're going and what we're able to do, with the idea, again, of trying to motivate you towards a collaboration in some format. Okay, so with that, let's go ahead and get started. And again, I realize not everybody does electrochemistry, so I want to remind you, if we use a redox molecule, we are going to energy probe different energetic states, right? And that in semiconductors, current only flows if there is an available state at that energetic position. All right, so what I showed you for the spectroelectrochemistry was our solid state approach with no redox molecule. Let's put ferrocene in our solid state electrolyte. This is something that we developed for my organic electrochemical transistor program for wearable sweat sensors. And so there was a very nice crossover between our organics and our perovskite sides of the lab. All right, so for MAPI, what I've done is I've drawn you your energy band diagram with respect to our spectroelectrochemistry approach that I just described. And then it's confirmed as well with photoelectron spectroscopy. And now we're going to put ferrocene inside the gel. All right, so that ferrocene molecule is able to be oxidized into ferrocenium, and then if there are available states, subsequently reduced back to ferrocene. Okay, and so what we're going to do is we're going to try and first look for acceptor defect states near the valence band. All right, and the way that we do that, okay, is again, we're going to start in a cathodic window in the middle of the gap. So what I'm showing you here is this red bar. And we're going to go just inside the optical gap of the perovskite. All right. The second thing I want to draw your attention to is, again, as we move in oxidation, we're going to push down towards the valence band. And what I'm showing you here is a cyclic voltammogram, but it is not one. Showing you how reproducible this measurement is. This is actually 5 cyclic voltammograms laying on top of one another. And you will see this over and over and over again. We do not observe any hysteresis with our measurement, meaning that it is non-destructive to what we're doing, at least in within the gap. Okay, so what we're going to do is a set of 5 cyclic voltammograms, and then we're going to slowly start to increase our potential window out in towards the valence band. All right, and so, oops, wrong window, sorry about that. And so here we go. Each of these is a subsequent set of 5 cyclic voltammograms. And what we can readily observe is now a couple of different key features. The first is that we have an increase with each potential window in our oxidation current, which is indicative of starting to observe more and more states near the valence band that are participating in some sort of oxidation event. All right. The second thing that we observe up here is now this increase in cathodic currents, which are associated with defects. And I'll show you why in a minute. The third thing that I want to call your attention to is where we're at on this energy scale. So ferrocene shows up at about 0.07 versus our reference electrode. In this window, we see no evidence of ferrocenium reduction back to ferrocene. All right, so what's happening here is we're going to oxidize defects as we come from about 0.4 in this case out to about 0.65. We oxidize defects and we then turn around and we're going to reduce defects. But because we don't see any ferrocenium reduction, all right, then we know that we have defect dominated redox behaviors. All right, now what happens if we push our potential window further into the valence band? Right, so we're going to increase our potential window and we're going to go into the valence band. Right, those colored CVs, same color code of what I'm about to show you. So we just talked about kind of the red to green, or about a current of from about plus or minus 5 microamps. Right, so now as we increase further and further our potential window, we push down into the valence band, and what we see is an increase again in our oxidation. Right, we push into the valence band, and now we know that we have ferrocene oxidation because when we turn around and come back, we now see evidence of that ferrocenium reduction. Okay. The other thing that I want to call your attention to is that we're not seeing an increase in defect behavior. All right. And so what does that mean? What we can do is we can integrate the area in our curve. If you remember, physics is that your currents, right, can be integrated with time, and this will now give you the number of charges that have participated in each of these reactions. So a coulombic analysis. And so in our oxidation wave, our total charges participate in the oxidation of defects, the oxidation of the ferrocene, as well as any irreversible oxidation of defects that we can't see. But what we can determine is how many of those defects, whoops, I'm sorry, too many screens. What we can determine here is the reduction of defects as well as the number of charges that participate in that ferrocenium reduction. All right. And so with that, if we put this on the coulombic analysis and we look at the scale, right? Here's our valence band, right? Right about here is our onset in our valence band, which follows an exponential behavior, which is exactly what you would expect from a Marcus Gerischer perspective. This is the semiconductor model of Marcus theory, effectively. Right? The other thing that we see is this region here, which is not exponential. And if we blow this up, you observe is actually a Gaussian distribution of our defects that is centered approximately 0.1 electron volts above our valence band. And the local maximum is on the order of about 2 × 10⁻17 defects per cubic centimeter. Right? So what this approach gave us, again, is energy resolution of our defects as well as quantification. Right? This is much, I also want to call to your attention, this is way beyond the resolution of our particular and most UPS types of measurements in order to observe defects above the valence band. All right, so that was our MAPI example. That's highly defect tolerant, or excuse me, it has a high defect density. Let's start to think about more device relevant, higher performing, more stable types of materials. And so where we switched now is to this triple cation formulation, right? And so I just want to call to your attention here the amount of lead iodide in this particular species. Okay, and this is predominantly what our defects are going to be in our acceptor defects, is it is going to be our mobile iodide, our redox active iodide components. Right? What I'm showing you here on the right are 3 cyclic voltammograms that compare that MAPI film versus our triple cation. And I see something very quickly, is these blue ones, these MAPI ones, have a very high current density compared to this triple cation. The other thing is that we don't see any of this ferrocenium reduction wave on this triple cation, right? And so what this really suggests is that we really have to think strategically about what our measurement is doing. Right. And so again, if we go back and we think about fundamental electrochemistry, when we do a cyclic voltammogram, what we're doing with time is we have this potential wave and we're monitoring the currents. But if we have a lower defect density, what that is equivalent of is that would be like reducing the concentration of our ferrocene in our gel electrolyte. And so as we reduce the concentration of our redox active species, our defects, it becomes harder and harder to resolve peaks from background charging currents. And what does that mean? Well, in an electrolyte, we have a high concentration of ions that are there to establish the electric fields. But when we apply a potential with time, this acts like a capacitor. And so those ions start to move around, back and forth, right? Like double layer behavior on a metal electrode. This causes a current, a charging current or a discharging current, right? The challenge with a low defect density is that that Faradaic current is much smaller. And so it sits on top of a high capacitive background, right? So what do? Well, we could try and just arbitrarily think about, well, I'm most interested in my Faradaic current, so I'll just background subtract that out. But again, as that gets lower and lower in terms of redox behavior, the ambiguity of where to draw your background gets harder and harder. So I've drawn two examples here for you, right? So our triple cation system is well established to have much lower defects, but we need a new electrochemical approach in order to resolve this, right? So in electroanalytical capabilities, what we do is we change our waveform. And so instead of just having that linear sweep that we do in a cyclic voltammogram, instead what we do is a series of potential pulses on top of that. And what this does is this lets us dictate or decide when we want to sample that current, right? And so we're going to still do the same, go across the gap of the perovskite into the valence band, but now we're going to do this with this potential waveform. And what that lets us do is basically choose time periods where we still have a substantial amount of our Faradaic current, which changes as 1 over the square root of time, but it lets us get rid of that capacitive charging current, okay? And so what happens now is this effectively, the waveform does it's a non-arbitrary background subtraction for us and greatly increases the resolution of these current peaks that we're observing. So we're going to do differential pulse voltammetry on the triple cation, now looking at acceptor defects, now with increased energy resolution and sensitivity to those defects. And this lets us greatly lower our limit of detection. And so I'm not going to go through all of the CVs and the analysis again, but what I can show you is definitively that we have, again, the same type of idea, defect reduction when we operate within the gap. And then when we push down into the valence band, now we're able to observe the reduction of the ferrocenium, as well as now the reduction of a triiodide species, which we confirm by putting a little bit of iodide into our gel. And so if we put this all together, now with respect to ferrocene, we know where the triiodide species is, as well as our defects, and we're at a resolution on the order of about 2 times 10 to the 15. So 100 times lower than what we were on MAPI with a cyclic voltammogram. Okay. So that's what we can do. And now I want to give you just a couple teasers about where we're going. And I'm seeing a couple of chats pop up here, so I'm hoping we have time for questions. All right, so we've really been trying to think about how to advance our measurement capabilities. Right, so where are we at? Our state of the art is we're below 10 millivolts or 10 millielectron volts, if you will, across the entire gap. I showed you acceptor defects. We can also do donor defects near the conduction band. All right. We can go across 6 orders of magnitude now. We're down to 10 to the 12th, and I'm going to show you an example of that. Limit of detection in our differential pulse voltammogram approach changes, and it's a little bit material specific because we have to balance that capacitive current versus that Faradaic current. This has been verified. Everything that I've shown you so far is samples that are prepared in our group, but we have verified our approach on industry relevant prepared samples, and that our defects that we're measuring in our device are equivalent to what we're measuring for our industry partner. And again, I'd like to really illustrate that we're interested in trying to do some sort of round robin with the community where we could compare the defects that we're able to measure electrochemically across a number of different relevant photovoltaic materials, as well as their respective device performance. Okay, so I told you we're able to do donor defects. This is under review right now, but I will tell you that we use 2 different types of redox probes. Both of these are a 2-electron process, and this allows us to go near conduction band, but also to push further in the gap, right? And when we put this together, right, this lets us draw a very, very intricate band diagram that we've not been able to do with any of our spectroscopy capabilities. All right, so I told you about starting with MAPI and air. We can see differences for a material that has been exposed to air versus not. We can do this approach in the glove box. All right, I talked to you about the triple cation. I showed you the 10 to the 15th acceptor defects, which also has higher donor defects. All right, likewise, if we eliminate the methyl ammonium, right now we're down to about 10 to the 14th. Again, this is all on just a transparent conductive oxide. All right, but that we're not able to detect any donor defects for this particular type of material, right? The other thing we've been really thinking about is saying, well, if we're going to pitch this as a device relevant capability, and then we do all of this defect quantification on transparent conductive oxides like FTO or ITO, how device relevant are we? And so I want to show you a little teaser. We've pushed this now. We can now get defects when we have a half-true half-device stack. So this is FTO, or excuse me, ITO, nickel oxide, and then our perovskite. And you can see now that we have the energy resolution with respect to the valence bands and the defects of our perovskite. And again, emphasizing that we can see defects and how these defects and these states change as we go from above gap and into the valence band. Okay. The other thing that we've really been thinking about is how do defects evolve with time? And that was where I started. And so what we've done is we've started thinking about putting our materials in a degradation chamber. So this example is an AM 1.5 with 5% humidity and at 60 degrees. And we do not encapsulate in any way, shape, or form. All we do is literally just make the films and put it in there and pull them out. And so we can see how defects change 4 orders of magnitude within an hour under these particular conditions. But the other thing that this lets us do is really start to establish the chemical pathways of how detrimental defects evolve. And so I want to call your attention here to the fact that at about an hour, what we see is a decrease in defects because the type of defect that we're observing has changed. Its energy level has changed into a different chemical species. All right. And so what happens now is that new chemical species lies within the gap of the perovskite, and it's at a different energy level, but it has a much broader but shallower defect density. And so that's why it looks like it goes down. Okay. And again, I showed you that this is on a transparent conductive oxide, but we can also do this on HTLs or ETLs. All right. Other things that we're doing, we are able to do because of the power of electrochemistry. It doesn't have to just be in a UV vis, and it doesn't have to just be in the lab. This could be involved with synchrotron radiation, right? We could do AM 1.5 and light bias so that we can actually monitor how the defects are evolving, right? And then, like I said, we could involve synchrotron. So we've done this as well to look at how the structure changes with different degradation conditions under, again, relevant electric fields with energy resolution and quantification. My other favorite thing about electrochemistry is it really transcends across length scales. And so what I've been showing you is what I would call a macro scale measurement, right? Maybe on the order of about a square centimeter. But there's no reason why we can't do this at the nanoscale. And so that's what we've been working on as well with Office of Naval Research Support, is building the capabilities to do basically electrochemical mapping of the perovskites to try and look at some of these different facets and where do the defects truly lie in space. And then the final thing I want to throw out there is that we're moving towards using photoelectron spectroscopy coupled with our electrochemistry or electrical capabilities. So what this is going to truly let us get is chemically resolved electrical measurements under lights, under applied electric fields. But again, what are the chemical species definitively? Like, we're pretty sure that we know what they are from our electrochemistry, but this will allow us to watch the dynamics of how those chemical species at the surfaces evolve. And so with that, again, We're really looking forward to hearing from you. And I want to thank you for your attention and thank the Office of Naval Research, as well as the Department of Energy and the Solar Energy Technology Office for the supports. And I'd be happy to take any questions.
Thanks, Erin. Just a reminder for everybody, we're going to use the Q&A tab to take questions. So that's that double speech bubble button on the bottom of the screen. Click that, pop it open, and type your question in there.
Yeah, looks like we have a lot of people on the line. But yeah, please type in your questions there, and I'll address them to Erin as they pop up. But maybe, because I know everyone's typing a question in right now, and they have all these questions they want to ask. So, but I'll start it off so that they have some time to actually type it in. So, Erin, thank you for the talk. That was really great. It was a lot of really interesting electrochemistry. And one of the things, I want to take a step back. I wanted to give a little bit of perspective towards some of the industrial members that were here, because I see multiple people from different companies on the line. Can you give us a little bit more perspective on terms of, essentially the application of this in line, right? So can you give me some perspective in terms of timelines on how long these measurements take, in terms of how destructive it is, what sample size required, those kind of things, just kind of gives, if you were, if you had your own perovskite solar cell company, how would you implement it? Those kind of things. Can you give us some perspective?
It's a great question. And that's actually the part of the focus of our CETO award is, and then where these cartoons come from, is that we're trying to develop basically a robotic arm. So as you can imagine, if you were going to do roll-to-roll coating or blade coating, et cetera, of the perovskite, right? But one of the things that we thought would be useful is, can you use the electrochemistry to monitor the perovskite as it's either drying or evolving or etc. And so what we want, or if nothing else, can you use it as just a quality control mechanism? And so that's one thing that we're very interested in hearing from industry as well as academics is how fast would you be willing to tolerate this? Again, we can always go faster, but then we lose the energy resolution. So if you've set your heart on one particular perovskite formulation, we fully believe that we can, with characterization, we already are going to know what the defects are that we're looking for. All we're looking for is, are they changing? Did something happen in the ink? Right? Do we have a bad batch or something like that? And so this would let a manufacturer do that. The other thing that we're interested in, like I said, is degradation. And so can we track how defects are evolving? And so we accelerated it just because we don't want to wait a long time. And so we didn't encapsulate, but you could imagine that if we could encapsulate the device and monitor the power conversion efficiency for thousands of hours and then open up the device and look at it, then we could start to see, well, what are the defects that have formed?
Yeah, no, that's great. Yeah, no, I know, I totally understand. That's definitely one of the big challenges in the field is as we degrade these in a faster way, because we don't have 20 years to wait. Yeah, what are the defects that we're making? How do we characterize them? So then we can come up with the solutions to prevent those kind of defects from forming. That's really great. Cool. No, I already see some questions popping up, so that's exciting. So let me see. We'll start from the top. So it says, what challenges did you face transitioning from TCO perovskite measurements to TCO HDL perovskite half stacks? For someone that's not well versed in chemistry, they want that little caveat at the end too. So.
Yeah. So let me see if I can. I'm pretty sure. Nope. Let's just talk about a band diagram, right? Is that when we had just the ITO and the perovskite, right? You can really treat an ITO or an FTO as effectively a metal electrode. It's got enough states at every single energy level that it can participate in holes and electrons going across that interface, right? But when we think about the half stacks that we use in photovoltaics, we use these HTLs and ETLs to purposely create a preferential pathway. Right. What we'd like to do, for example, is the light comes in, you create the holes in the electrons. You'd like to pull the holes out of the perovskite through the HTL into the ITO. What you would want to prevent is the injection of holes from the ITO through the HTL into the perovskite. So you've already created an asymmetric interface for charge transport. And so then you want to try and ask a question where you use a measurement that thinks about oxidation and reduction on a system where you've designed a preferential highway for charges.
Mhm.
And so we let's see, I think that was on 42. Nope. So when we started to make the device stacks, right, our distributions are very different. Instead of that Gaussian distribution of where you would see the defects, right, we have to be willing to sacrifice some of that type of resolution in order to now look at the interface. But what we gain is the ability now with all of these different interface modifications to truly see how do these impact the device in operando using that half cell approach.
Great. No, thanks for the question. It's a good question. Let's see here. Jeff Christians asked, thanks for the talk. Great technique development. But you mostly showed valence band effects, but conduction band effects in some of the formulations. Can you comment a bit more on the conduction band? And what are the differences?
This one, I think. So I predominantly showed the acceptor defects is because that's what's published. The donor defects are currently under review. And so I talked about the two different probes that we've used. And then the other thing as well is that I mentioned when I presented the slide was that the donor defects for this triple cation are about an order of magnitude higher than the acceptor defects. What are they? In this case, what we think they are is a under-coordinated form of lead. I'm not going to call it lead zero, but stay tuned. We have a really, really beautiful dynamic XPS, near ambient pressure XPS paper that we're about to submit as well. The other thing I will say is, if you're really interested in that, both Michelle de Kersmacher and myself are giving talks on it at Materials Research Society in a couple of weeks.
Nice. Just a little MRS plug.
Yes.
Yeah. Actually, speaking of which, I kind of brought up another question I had, which was, so obviously we can measure all the defects on the surface using these techniques, but trying to understand what is chemically going on. What is missing? Is it an iodine vacancy? Is it lead reactions? Do you mainly use XPS to characterize that, or is there other techniques that people could use to try to figure out? Okay, yeah, we see a difference, but what is that difference on the surface?
Yeah, and I think too the thing to remember is, especially too, is electrochemists. You know, we make a lot of chemical inference from a cyclic voltammogram, but it's not inference, right? There's a lot of theory and thought that goes into that. And so what's hidden in the background is the 45-page SI that shows, you know, is it iodide or is it bromide, right? And we know that iodide and bromide have different oxidation potentials. And so you can put iodide in and you can put bromide in. And then what you see in our case, for example, in the triple cation, is that those defects peaks do truly go up when you spike it with a little bit of iodine, and that the bromide is not participating at all. You have to basically destructively oxidize that perovskite in order to get the bromide to come out. And so there's those kinds of tricks, but to how the question was phrased, I do like to use the chemical verification as well in concert, because they give you different information, and that lets you understand the puzzle a little bit better.
Great, thanks. Yeah, keep the questions rolling in. I think we still have a little bit more time. So let's see. Another attendee said, thanks for the great talk. Would like to know how this technique can be applied for coating techniques, since it needs a reference electrode, solid polymer electrolyte. So I think they're discussing specifically the CV and stuff like that. So.
Yeah, and so that's what we've been thinking about. So you can imagine, right, the electrochemical cell effectively is that gel and whatever we stick in it. And so there's no reason why you can't come over, drop your little electrochemical cell down, because it's just it's a solid state electrolyte, do your measurement and then pop it back off. And so that's really where we're trying to go with this idea of a robot, is can the robot do the spatial types of measurements that one would start to think about? And then hopefully, if we have time, is can we try and do it as the film is moving. So then the robot would probably be moving along at the same speed as the web, do the measurement, pop off, throw away, get a new one, come back, and go forward.
Great. Yeah.
So I was going to say too, since we do have a number of industry people online, all of this concepts is patented with U of A. And so if you're interested in this, we would love to connect and work with you. So.
Great. Yeah, no, I also assume this is probably pretty sensitive to, because I know one of the biggest problems, especially in academia, and I'm sure a lot of other industrial partners too, is reproducibility within perovskites. I'm sure it's pretty sensitive technique for trying to characterize how reproducible your processes are,
and that's something that we've started doing too. So we're obviously way behind on submitting papers, but we have one where we did a round robin within our lab. So everybody made the same formulation and then characterized each other's. And so now we can have, for the same formulation, with those standard deviation bars are not just, oh, we did the same, we made 5 films and characterized it and that was all Michelle, but instead everybody made one. And, you know, we use different people who had no electrochemistry experience and all of that kind of stuff as well. So.
Yeah, especially surface states are always so hard to actually understand, so it sounds like a great technique to kind of get that perspective as well. And,
yeah, absolutely.
And pair that with some more bulk measurements and stuff as well. So.
Yeah, well, and then ask the question about additives. What's an additive really doing? How much do you need at what concentration? You know, and then couple with all of the other really great fundamental science. It's been a lot of fun.
It's great. Let's say we get another question here. Thanks for the talk, Aaron. I assume you have many defect types, densities, and energy levels. Is it possible to isolate the impact of a given defect on performance and stability to prioritize which defect to focus on for performance improvement?
That's a really great question. I don't have the answer to that. It's because I don't think we know yet. I think we all have pretty good ideas of which particular defects are the challenge. What I will say, and that is kind of too how we approached our degradation study, is we have devices that are in the chamber at the same time. And so you can monitor the device change, and then we also have our half cell stacks and you can look at that. But even there, trying to draw a correlation is different because when you have the full device, right, you have different oxygen, water permeabilities across the different layers. And so, you know, there's still some challenge. I think to my plug is how would we do that is what if we tried to do this round robin? What if we, you know, all of us got together, everybody's making devices, you know, we can do the electrochemistry and let's ask where those defects are and then put that across the you know, try and correlate that with device performance and stability.
Yeah, no, I think that's a huge challenge within the field, and something that this has potential to help answer some of those questions. But I think, yeah, you're right. Just it's going to require a lot more devices, a lot more correlation, a lot more passing back and forth and stuff like that. So, no, that's a great question. Any other questions from the participants?
Yeah, let's give it just like another 30 seconds. If you've got a question, get it in. Otherwise, I think we can wrap up.
I'm gonna go back to my list, make sure there's nothing else that I wanted to ask before we leave. Oh, I guess let me just ask one while I give people a little bit more time, and then we can wrap up. When you were talking about triple cation versus MAPI, which is funny, right? Because you know MAPI much more defects, triple cation much less defects, which is kind of funny because you think a little bit more complex system would actually be have more defects. But was the triple cation also multi-anion? So is that iodide bromide? Oh, okay.
Yes.
Yeah. And then you can also use some special, like some of your CV background or whatever to actually start figuring out whether it's the iodide or the bromide and stuff like that, and where that's affected. Okay, that's cool.
Yep, absolutely.
Cool. Any other questions from the participants? All right. Well, we're like 50 minutes, so pretty good. Thank you, Aaron, for the great talk. That was great. Um, hopefully you get a lot of emails from people that want to participate with you and stuff like
I
that.
hope so. Thank you, everybody, for your attention. I really appreciate it.
Yeah, thanks everyone for attending. And just a reminder, we will put the recording on the US Map website on the webinars page in probably about 2 weeks once we get the video processed and uploaded. Thank you so much, Aaron.
All right. Bye.
Great. See you, everyone.